Indecomposable continua in exponential dynamics.
Hello everyone, I'm going to tell about indecomposable continua in exponential dynamics. So first thing is to define the exponential map. This is the function e lambda of z equals lambda e to the z. And lambda is some complex parameter. And standard thing which we can do is to define the partition of the plane. Every set is the strip with height 2 pi, and we have countably many such strips. Every boundary of every strip maps into negative real half axis. And with such partition, we can define the itinerary of a for every z. We can define for every z we can associate. We can define itinerary for every z. A sequence of integer is an itinerary if and only if. For every k, the kth iteration of z is in the strip given by the kth element of the itinerary. And on these itineraries, we define, on the sequence, we define the shift map, which works like this, that we just erase the first entry. And we say that the itinerary is bounded when the sequence is bounded. Otherwise, we say that this itinerary is unbounded. And we define the special subset of itineraries. We call it exponentially bounded itineraries. We define the function ft, which is a real function e to the t minus 1. And itinerary is exponentially bounded when absolute value of every element of itinerary is smaller than iterations of some of this function on some x. So there exists a and x positive that for every k such bounds is satisfied. We call the points which tends to the infinity escaping points. Okay, and now we define a tail of a hair. Tail of a hair is the curve which is in the complex plane, and this curve is indexed by itineraries S, and this curve must satisfy 3 conditions. The first condition is each point on the curve is an escaping point. Every point on the curve has itinerary S, and the limit of this curve, the limit of the real value of the curve, of the points of the curve when the argument tends to the infinity is plus infinity. It means that this curve tends to the infinity, let's say to the right. And we can see that since every point on the curve has itinerary S, this curve gamma lies in the certain strip given by the first entry of the itinerary. Okay, so we have now a powerful theorem, which this theorem is in fact the composition of a few theorems. Schleicher and Zimmer proved that, first of all, if we define the set I of S, which is the set of all points sharing given itinerary, this set is non-empty if and only if the itinerary is exponentially bounded. Moreover, every such set, IS, if the itinerary is exponentially bounded, contains tail of a hair with itinerary S. And using the equation, I will write it. If we use such a functional equation, E lambda on gamma S equal gamma S on T equal gamma shift of S on F of T, we can extend all these tails and construct whole hairs, which are curves parametrized by half line 0 plus infinity. And the main thing to know is that every escaping point, this is the characterization of escaping set of escaping points. Every escaping point must satisfy one from the 3 conditions. The first is that this point lies on the hair. Every escaping point lies on the hair, or point is the landing point of the escaping hair, it's the landing point of the unique hair. It means that there exists, if this is the hair, there exists a limit on this side of the hair, and this is the endpoint or the landing point. Or there is a third condition that the point, escaping point, maps after finitely many times onto the hair on asymptotic value 0 lies. Okay, so in general, these hairs can cross the boundaries of our strips, but this is not the case for real lambda. For real lambda, gamma OS is a subset of iOS. And for lambda, which are not real, in fact, we defined the itineraries in slightly different way, but the idea is the same. We can define the itinerary in slightly different way. We can divide the plane into not strips RK, but into sectors, which we can create by taking the reimage of the hair on which 0 lies. But this is only the digression. And I want to say also that the existence of hairs was investigated earlier than Schleich and Zimmer. For example, by Devaney and Krych, but for only such parameters, real parameters lambda, and by such 6 authors, but for general lambda, complex lambda, but only for bounded and regular sequences. Regular means that these sequences that not contain any zeros. And if we have a hairs, we can construct using these hairs indecomposable continua. So in this case, this is the case where the so-called accumulation set is very simple. But for some hairs, the accumulation set is not of this form. This accumulation set is, in fact, indecomposable continuum. And now I want to present 5 theorems about indecomposable continuum in exponential dynamics. But before that, I want to say what is continuum. Continuum is just this non-empty compact connected space, and the indecomposable continuum is a continuum which cannot be written as the sum of 2 proper subcontinua. And for every hair gamma S, we can define the accumulation set, which is also called landing set, as a set of all possible limits of gamma. Sorry, this should be TS, or here only gamma. A gamma of Tn, where Tn goes to 0. Okay, so the first theorem is by Devaney, and this theorem states that if we take the set of all points which for which all iterations stays in the strip, this is the intersection of R0 strip with upper half plane. So for points which stay every orbit stay in this set from 0 to pi. This set is not in the composable continuum, but there is a compactification of such set that makes it in the composable continuum. Another theorem, and this is the most important theorem during this talk, is like this. We have a lambda bigger than 1 over e and real, and we have a sequence of blocks. Block is the finite sequence of integers, and we suppose that in every such block there is at least one non-zero integer, and we also suppose that there is a constant common for all blocks, that absolute values of every integer in every block is bounded by that constant. So in other words, if we create the itinerary from these blocks, this itinerary is bounded. And under such assumptions, we can find a sequence of natural numbers such that if we create such itinerary, 0 with some index is the block of 0 with length given by the index. We can find a large enough block of 0 that the set IS for such itinerary is the indecomposable continuum together with the point at infinity. And also this is the closure of the hair and the accumulation set of the hair. Another theorem, Devaney-Harke-Rocha, for lambda equals 2 pi I. There is different situation. I mean, I of S can consist of continuum and the of the hair and the continuum, which is the accumulation set of the hair, or there may be two pair of the curves which accumulates on itself and on themselves, on itself and on each other. And in this case, the accumulation set of these two curves is in the composable continuum. The fourth theorem is by Rempe. For general lambda, only if the singular value 0 escapes or is the landing point of the hair. There exists a hair for which accumulation set contains hair itself, and this accumulation set is an indecomposable continuum. And the last theorem is the newest one by Fu Chang. Again, lambda equals 2 pi I. And now there exist non-landing hairs. Non-landing means that this is not this case. That the accumulation set is bounded by this accumulation, but this accumulation set is either in the composable continuum or the Jordan arc. And there are a few things in common between these theorems. In every case, for every lambda in our theorems, the Julia set of E lambda is the whole complex plane. And all theorems, at least all theorems without the Rempe's theorem, construct itineraries which are bounded. For Rempe, it's harder to say in a few words if the itineraries are bounded, because lambda is can be not real, and for not real lambda, the zero can have unbounded itinerary, and in Rempe's construction, these itineraries which he construct depends on the itinerary of 0. And all of them uses in the proofs Carey's theorem, which says that if we have a continuum on the plane, one-dimensional, and this continuum is the closure of some curve, which accumulates on itself. So we have, it means that the convolution set contains this curve. And we also assume that this continuum does not separate the plane. It means that the complement of this continuum is a connected set. Then this continuum is indecomposable. So the main thing to prove in all these theorems is to prove that the accumulation set of the hair contains the hair itself. And now I want to present the theorem I managed to prove recently, which is very similar to theorem of Devaney-Harke, which looks almost the same, but we can drop the assumption that these T blocks are there is a common constant which bounds these blocks, and the result sounds the same. We can construct such itinerary that IS is an indecomposable continuum. And I will shortly tell about the proof. So first thing to do is that I choose some special subset of unbounded itineraries. I choose for fixed M and P, I choose the itineraries which grows not faster than some linear function. And I also, but this is nothing new, I also suppose that, assume that itineraries do not end in sequence of zeros. And this assumption allows me to not bother about this third case in Schleicher-Zimmer classification when the sum point maps after finitely many times on the hair on which 0 lies. Okay, so I choose such subset of unbounded itineraries. I mean, this set contains all unbounded and also bounded itineraries. because this condition is quite simply, and this was the first thing which comes to my mind when I try to try some approaches to this problem. And these itineraries grows. You can imagine that if the itinerary grow, if the slower, then the proof should be easier. So I choose such itineraries. And I prove similar statements as Devey and Harke in their proof, but not for bounded itineraries, but for itineraries from such a set. And the idea of the proof is basically the same. I prove the analogous of the statements. And then this allows me to construct unbounded itineraries with blocks of zeros for which set IS is indecomposable continuum. I want to talk a little bit more about the proof of the another second theorem about the dynamics in the set IS. So Devey and Harke prove that for every bounded itinerary, there is a unique point in set IS such that this point has bounded orbit. All other points have omega limit sets which are infinity or the orbit of zero if infinity. Points which lie on the hair, of course, have omega limit set in this form, and every point which is different from ZS and which not lie on the hair have omega limit set in this form. And we have also a theorem by Ljubich that for E1, but in fact, it can be generalized to every lambda bigger than 1 over E, the omega limit set of almost every Z with respect to Lebesgue measure is of this form. And for unbounded itineraries, the various things can happen. For example, there are itineraries, unbounded itineraries, that the whole set IS looks like this, and all points, even this landing point, is escaping point. But I managed to prove some result which states that there is some special point for itineraries of the form like previous, so of the block form 0, T block, 0 block, T block, 0 block. So the assumptions are the same as in the theorem about indecomposable continua, and the result is that we can find blocks of 0 large enough that for such itinerary in the set IS, there exists a unique point which has the omega limit set, which the omega limit set contains at least one of the points Q plus, Q minus, and I skip it. For E lambda, lambda bigger than 1 over E, in strip R0, there are two fixed points, Q plus and Q minus, and one of them is in the upper half plane, and one of them is in the imaginary part negative. And for every other point, which is every other point, it means that we are not this special point, and we are not on the hair. The omega limit set is of this form. Okay, so now I want to show the sketch of the proof, and the first lemma is as follows. We have an itinerary from sigma MP for some fixed MP, and there is a constant which depends on this MP, such that if we are to the right from the line given by this real value, the omega limit set of all points with such itinerary is orbit of 0 with infinity. And the proof is this is in this picture. Suppose that we have first is that we the notation segment Tn is the segment between nth iteration of 0 minus 1 to n plus 1 iteration of 0 minus 1. In the first step, if we have z for n big enough, if we have z for which the real value is in this segment, then we can show that after k iteration where k is at most n plus 4, we do something, and after k iteration we lens above or below the next t segment. how we can do that? So if Z is from this, Z has itinerary from this set, then we know that there are some bounds of on the imaginary part of the image of Z. And if n is big enough, then image of Z lies on the big circle. So it it has to lies on this part of the circle on this. So suppose that suppose that we are here, and if we are far to the right, then at least for few iterations we know how the iteration looks like. We go near to the zero, then near to the image of zero, and for some time we travel close to the orbit of zero, and then we can calculate that in fact we land here. If we are at this point, we can again go to the right or go to the left, and the whole process repeats. And okay, but we are here. The main question is, we know that there are some bounds of the image of this e to the k of z on the imaginary part. And the question is if that bounds of the imaginary part of the image of this point are good enough to repeat this process. That we can repeat this process, and after at most n+5 iteration, we are in the t(n+2) segment, and we again have good bounds on the imaginary part. And the answer is yes. For itineraries with linear growth, we can do that. Okay, so we in some sense know that if we are far to the right, then the omega limit set for such points is as we want. Now some notation. So we can add zeros to our sequences to have this property that if we start our itinerary from the zero block, then it is from the set sigma MP, and this is the same MP as the original itinerary. Because there are no bounds on the integers in TJ in T blocks, but these T blocks are are finite. So we can add a lot of zeros, and it doesn't matter that some integers here are big. Okay, and BJ is the first non-zero and first entry of TJ block, and we can assume that this is non-zero. EJ is the last. A is the such iteration that the itinerary looks like this, as D is such iteration that such number that this iteration, the itinerary looks like this. So begins with the last element of the T block. And we can now prove the lemma that if we are not on the hair, then if at least for one J, we are outside to the right from the C or to the left from the minus C at this particular moment, DJ iteration, then the omega limit set is equal to orbit of zero again with infinity. And again, the proof is by the illustration. Okay, so we have a point which is to the right from some big C, or the second version, we are to the left from the minus C. And our itinerary looks like this because this is DJ, so our itinerary begins with EJ. So if we take the E on this point, we have this point or this point. If we have this point, then we are done because first of all, we are to the right from the X of MP. And what is the itinerary of such point? This is this itinerary without this first entry. And we assume that if we begin our itinerary from our blocks of zero, then this is from sigma MP. And we use the previous lemma. But what happens when we, for example, go to the left? So we know that after for some time, we travel close to the orbit of zero. and we can prove that at some time we cross this x of MP, but we waste some iterations, and our itinerary, from our itinerary disappeared some zeros. So this is the problem. And solution to this problem is that for fixed MP, this x is fixed. So we can find n such that e to the n of 0 is the first iteration of 0 to the right from x. So we have to remember this n, and we just simply modify our itinerary by adding, I think, n plus 1 or n plus 2 zeros for to every such, adding extra zeros to every block. So after, let's say, wasting this n plus 1 or n plus 2 zero, this itinerary without this ej is again from sigma MP for the same MP for which x was derived. And then we use the previous lemma. So it means that every point, okay, so maybe such definition. We represent DJ iteration of E as we take some iterations of E and compose, let's say, a block of E iterations from each. And the phi j is like the inverse function of every such block. In fact, this is just a composition of logarithms, and these indexes Q are such that we reconstruct our itinerary. So we define rectangle, which is some part of arcade with closure, which is between C. Oh, sorry, this should be absolute value of C. So like in this lemma. Then if you take the intersection of such pre-images of every rectangle, we can conclude that every point which has different omega limit set than orbits of 0 plus infinity has to lie in this intersection. Because if there is a moment dj that our points iteration, dj iteration of our point lie to the left from the dj set or to the right, then we use this lemma, and this point has a itinerary, omega limit set of this form. And so now we only want to prove that this set is in fact non-empty, contains only one element, and we'll see that this element has omega limit set which contains at least one of these points. So to show that this is that contains at most one element, we can do it easily with such a lemma, that if we have a composition of our function is the composition of E, the derivative of such composition with absolute value is at least like the absolute value of image of this function. And our for us, I will go back. DJ is such that the image of such composition lies in the strip with number EJ. But we assume maybe EJ, but we assume that this is the last and this is non-zero element of block TJ. So this derivative is at least pi because we are not in the strip R0. So the derivative of P is less than 1 over P. And when we compose on this set, when you compose this function, we have a collection of nested sequence with diameters which tends to 0. And this set, if it's not empty, then contains only one element. It's almost the end. But we want to prove that this is non-empty and in fact contains one element. So we have to prove that this is in fact nested sequence, that Gj is a subset of Gj minus 1. This is the same as asking if phi j on Dj is the subset of Ej minus 1. And the proof is on this image. So firstly, let's focus on these red shapes, B plus n. We also define B minus n, which is the reflection of this set in the lower half plane. This is almost rectangle because we cut some parts from it. This part is exactly the image of this left half plane. This is the circle around the 0. And this part is the image of this. This is not the circle, but something close to the circle. And we cut every such image if it's needed. And we can prove that if we set the bounds properly. This is the of this rectangle, left and right bound. This is the, for example, some proper choice of these bounds. Then the image of B plus of n covers B plus of n. So if we go in the second direction, if we take the logarithm, which takes us from the complex plane to the R0 strip, so logarithm L lambda 0, then we are inside the B plus of n. But this is not enough because we want to be inside the interior of the B plus of n. But for every point on the boundary of this set, there is a number which depends on n, such that after that number of iteration on this point, we are out of the B plus. For example, if we are here, then image is somewhere here, then here, 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 and we are out. So in fact, there is m such if we compose logarithms and we evaluate it on the B plus of n, we are inside the interior. And using some hyperbolic metric and Schwarzschild lemma, we can prove that if we compose these logarithms, we can be arbitrarily close with such set to the fixed point Q plus or Q minus if it's in the set B minus. So now this is the last slide. We have our set DEJ, which is the rectangle. And let's suppose that TJ looks like this. This is the first entry is BJ, the last EJ, and something between. This is only the notation. So we create the CJ as we take the logarithms with respect to these entries, and we have some bounded set because the EJ is bounded, and some of these entries are not 0, but if there is 0, this is also not a problem. We have some bounded set CJ, and for such bounded set, we can find n big enough that this set is inside this circle, is inside the image of B plus of n. And now we can apply the logarithm L lambda 0 to the CJ and apply these logarithms as many times as we want, and we get such a set, which is arbitrarily close to the Q plus fixed point. This is the set L lambda 0 to the nj of CJ, and the itinerary of points in this set is 0, 0, 0, 0, 0, 0, and then this block. So the last thing we want to do is take the logarithm, which takes us to the strip R aj minus 1. So our itinerary begins with the last entry of previous T block. And since we are close to this number, we are close to the pre-image of this fixed point. So we are inside, if we are close enough to this point, we are inside the DEJ minus 1 rectangle. And this is what we want to prove. And from the construction, we see that this point which lies in this intersection of set GJ has orbit which is arbitrarily close to the Q plus. Q plus if the BJ is positive, Q minus if the BJ is negative. So if the infinitely many BJs are positive, then Q plus is inside the omega limit set of this unique point. And if the infinitely many BJs are negative, then Q minus is inside the omega limit set. And these two cases can happen at the same time. So this is it. Thank you for your attention.
Are there any questions or comments?
I have a question. So, if I understood you correctly, you can prove the existence of indecomposable continua for the linear growth of itineraries.
Yes.
What about something slightly faster? So, in quadratic growth, polynomial, exponential.
The short answer is I don't know, but I think a little bit about it. So I see that in every step in my proof, there is a space to improve it. But at the end, in the construction presented by Devin Harke and I reconstructed, we still add a lot of zero and any point, I don't control how many zero we add. So when I writing my proofs, I just don't care about how many. I just add zeros every time when I want. Yes, but the sent, even if I prove that for some quadratic not itinerary something is true, that the statement is still the same because this sequence, the entries of T blocks can be whatever I want. Even if I compose this itinerary from only T blocks, this itinerary can be not even exponentially bounded. I just kill the growth firstly, I just kill the growth by adding zero, and then I have a sequence which is from my set sigma MP, and then I just do what Devin Harke presented in their proof.
Any more questions? Yeah.
I mean, so you can basically you consider there is some here, and the accumulation set of this here is in the composable continuum, right? What if you consider the corresponding to this ray to this here is a parameter ray in the parameter space? Do you have an idea what's happening there? Maybe also the limit. Since that would be in the composable continuum or something interesting.
So you are asking what happens in the parameter space, not dynamical space.
If your singular value
Okay,
is
so I wasn't thinking almost anything about what happens in parameter space, so I'm afraid I can't tell anything.
yeah, just one more question. So how much do you think your approach would be generalizable? So how heavy is this usage of this exponential one function there? Maybe you could do it for some other functions with hairs, more general ones.
Yeah, so this is what I want to do, but I'm at the beginning. I'm just at the beginning of the process. I just finished this, and now I think I'm switching to the such consideration as you asked.
No, then let's thank Radosaaw.